We often think of artificial intelligence as, really cutting edge, something that just popped up recently.
Right, like it was born in a lab yesterday.
Exactly.
Yeah.
But this whole idea, the urge to create artificial beings, it actually goes back, way back.
It really does, astonishingly far back.
Think about ancient Greece. We're talking, what, around 700 BC? You've got the myth of Talos.
Ah, Talos.
Yeah.
The bronze man.
Yeah. And he wasn't just some lifeless statue. He was described as this artificial man, made of bronze, yes, but self-moving. He had internal workings, almost like rudimentary programming patrolling Crete.
And it's fascinating because Talos isn't alone. You mentioned Hephaestus earlier, right?
Yeah.
He crafted Pandora, but also these golden female servants who could move and operate on their own.
Right. Those automated...
And it all points to this, well, this really long-standing human fascination. It's not just about copying life, but about creating things that can act autonomously, following instructions, doing tasks, almost like a very early concept of an intelligent agent.
That's a great way to put it. An early intelligent agent.
Yeah.
And that thread, that fascination, it really does run through history, doesn't it?
Absolutely.
So that's our mission for this deep dive. We want to follow that thread from those, ancient myths and dreams all the way up to the AI and the agent systems that are, frankly, reshaping our world as we speak.
And we've got some solid material to guide us. We have these really detailed notes that lay out the timeline, the key people involved, the big ideas that shifted the whole field.
Okay.
Plus, there's a briefing document that summarizes it all really nicely. And for anyone listening who wants to dig even deeper, there's a study guide with definitions and context for the core concepts we'll be hitting.
Perfect. So for you listening, our goal here is to give you a clear and hopefully really engaging picture of how this all evolved. We want to highlight the breakthroughs, those aha moments, and the folks whose thinking really pushed AI forward.
Think of it as maybe a shortcut, getting you up to speed on AI's history without needing, a PhD to follow along.
Exactly. All right, so to understand where we are now, we need that foundation. Let's lay the groundwork. Where does the modern story really kick off?
Well, before we even get to machines, there are some philosophical roots that are, I think, pretty important. You have ideas like rationalism, this emphasis on logic and reason suggesting intelligence could be formalized.
Okay, so not just some magical spark.
Right, and later, computationalism becomes huge. This is the idea that essentially what our brains do when we think isn't fundamentally different from what a computer does when it computes. It's manipulating information based on rules.
Ah, so the mind is a kind of computational process. That definitely opens the door.
It really does. It suggests that maybe, just maybe, we could replicate those processes artificially.
And then people actually started building things, machines that calculate. Tell us about Pascal and Babbage.
Sure. So Blaise Pascal, mid-17th century, he builds the Pascaline. It's really the first practical proof that you could mechanize math, a calculator, essentially.
Okay, a mechanical calculator.
But then Charles Babbage, in the 19th century, he takes it way further. His difference engine was impressive, but the analytical engine, that was visionary.
That's the one he designed but didn't fully build, right?
Exactly. Designed before 1852, unbelievably. It had like an arithmetic logic, unit, memory, programmable instructions using punch cards. It was conceptually a general-purpose computer, decades ahead of its time.
Just mind-blowing to think the blueprint was there so early. And connected to Babbage, we absolutely have to talk about Ada Lovelace. Her contribution was incredible.
Oh, absolutely essential. Ada Lovelace didn't just understand the analytical engine's math capabilities. In her notes from around 1843, she wrote what many consider the very first computer algorithm intended for that machine.
The first program.
Yes. But maybe even more profound, she saw that the machine wasn't limited to numbers. She realized it could manipulate symbols representing anything, not just quantities. That foresight, it hints at the entire future of computation and AI.
Wow. So she grasped that potential for symbol manipulation way back then. Okay, fast forward a bit. Mid-20th century, Alan Turing. His work seems absolutely crucial.
Foundational, no question. His 1936 paper on the Turing machine, it provided this elegant theoretical model of computation. What can a machine compute, fundamentally?
Right, defining the limits and possibilities.
Precisely. And then early 1950s, he directly tackles the idea of thinking machines with the Turing test.
Ah, yes, the imitation game. Can a machine fool a human into thinking it's also human?
Exactly. It gave a pragmatic, if debatable, way to assess machine intelligence, and people still argue about it today.
They certainly do. Okay, so we've got philosophy, early calculators, Babbage's vision, Lovelace's insight, Turing's theory. What was the spark? The event that really launched AI as its own field.
That would have to be the 1956 Dartmouth Summer Research Project on Artificial Intelligence. That's the moment.
Dartmouth 56. Who was there? Sounds important.
Oh, it was a powerhouse group. John McCarthy, he's actually credited with coining the term artificial intelligence for the workshop. Marvin Minsky, Nathaniel Rochester, Claude Shannon. Giants of the field, basically.
Wow. Okay. So what was their big, ambitious goal? What did they set out to do?
The proposal itself is kind of amazing in its confidence. It basically stated that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it.
Every aspect. That's bold.
Incredibly bold. It really set the tone for those early years. A huge amount of optimism that they could crack intelligence, maybe even within a generation.
That optimism fueled what's often called the golden years, right? The era of symbolic AI.
Yeah.
What exactly was that?
Right, the golden years, late 50s into the early 70s. And the dominant approach was symbolic AI, or sometimes called Duo-AI, good old-fashioned AI.
AI.
It was heavily influenced by Newell and Simon's physical symbol system hypothesis, the core idea that intelligence comes from manipulating symbols like words or concepts represented internally according to logical rules.
So knowledge is symbols. Thinking is rule-based symbol manipulation, like high-level logic processing.
Pretty much, yeah. You represent the world in symbols, you write rules for reasoning about those symbols, and intelligent behavior emerges.
Okay, makes sense. What were some of the early wins using that approach? What made people so optimistic?
Well, they had some really impressive early successes. In '56, the same year as Dartmouth, Newell, and Simon unveiled the logic theorist.
What did it do?
It proved mathematical theorems from Whitehead and Russell's Principia Mathematica. That was a task people thought required human intuition.
Wow, okay. Proving theorems.
Yeah.
What else?
Then came their general problem solver, GPS, in '57. The goal was, well, general problem solving, using a technique called means-ends analysis, basically figuring out the difference between your current state and your goal state and taking steps to reduce that difference.
A universal problem solver. That sounds like the Holy Grail.
It was incredibly ambitious. And while GPS didn't quite achieve universal problem solving, it was a powerful demonstration of the symbolic method. Then, '58, John McCarthy develops LISP.
The programming language.
Yeah, LISP became the language for AI research for decades. It was designed specifically for manipulating lists and symbols, perfect for symbolic AI. Steve Russell did the first implementation, Tim Hart and Mike Levin the first compiler a bit later.
Okay, so the tools were being built too.
Definitely. And other successes followed. Herbert Gellinter's geometry theorem prover, also '58. Daniel Bobrow student program in '64 could solve algebra word problems given in simple English.
Solving word problems. That requires understanding language, doesn't it?
To a degree, yes. It was limited but impressive. And then, 1966, Joseph Weissenbaum creates ELIZA.
Ah, the chatbot. The therapist program.
That's the one. ELIZA was famous because it could carry on these, well, seemingly intelligent conversations just by pattern matching and using clever canned responses. It fooled a surprising number of people.
The ELIZA effect, right, where people read way too much intelligence into it.
Exactly. It showed how easily we can be tricked, maybe. Then, around the same time, late '60s, Minsky and Papert championed the idea of microworlds.
Microworlds,
Yeah.
like simplified universes for AI.
Sort of, yeah. The idea was, instead of tackling the whole messy real world, focus on a very constrained, simple environment, like the blocks world. Just a simulated table with different colored blocks.
Okay, the blocks world, I've heard of that. Who worked on that?
Key people were Gerald Sussman, Adolfo Guzman, David Waltz, Patrick Winston. They used the blocks world to make progress on vision, planning, natural language.
And that led to SHRDLU.
Yes, Terry Winograd's SHRDLU around 1970, that was a landmark. It operated in the blocks world, but you could give it commands in pretty complex English like pick up the red block and put it on the blue one.
And get to understand and do it.
Yes, and it could answer questions about why it did things or about the state of the blocks. It integrated language, perception in its simulated world, and action planning. Really sophisticated for the time.
Incredible. And we shouldn't forget Shaky, the robot.
Definitely not. Shaky, developed at SRI from '66 to '72, was crucial. It was embodied AI, a physical robot moving in the real world.
So it had sensors it could see,
It had sensors, yeah. It could perceive its surroundings, then use reasoning things like the A-search algorithm to find efficient paths.
like planning its route.
Exactly. And the strips planning system to figure out sequences of actions to achieve a goal, and then it would actually move and perform those actions. Perception, reasoning, action, all integrated. A true pioneer.
Okay, so theorem provers, language understanding in microworlds, a physical robot navigating rooms. The golden years sound truly golden. But then things cooled off. The first AI winter hit in the mid-70s. What happened?
Yeah, the optimism hit some hard realities. The first AI winter came about for a few reasons. One was simply overpromising and underdelivering. The early successes were amazing in their limited contexts, but scaling them up to complex real-world problems proved incredibly difficult.
They were brittle, didn't handle unexpected stuff well.
Very brittle. And the computational power needed just wasn't there yet for the truly grand ambitions. Then you had things like the Lighthill Report in the UK in 1973.
What was that?
It was a highly critical assessment of AI research progress, commissioned by the government. It basically said the field hadn't achieved much of practical value and questioned future prospects. It led to major funding cuts, especially in the UK, and had a chilling effect elsewhere, too.
Ouch. So unmet expectations and funding cuts lead to a downturn. But AI didn't disappear. The 1980s saw the rise of expert systems. What was the shift there?
Exactly. The focus kind of narrowed. Instead of trying to build general intelligence, researchers concentrated on creating systems that could capture the knowledge of human experts in very specific, narrow domains.
Okay, so ditch the grand goal for now. Focus on practical applications.
Pretty much. These expert systems typically had two main parts. A knowledge base containing facts and rules about a specific subject, like, say, diagnosing infectious diseases, and an inference engine, which used those rules to reason and reach conclusions.
Like encoding a doctor's knowledge into rule.
Essentially, yes.
Yeah.
And some were quite successful. Dendrol was an early one, late 60s, early 70s, helping chemists figure out molecular structures.
Okay.
Then MYCIN, mid-70s, for diagnosing blood infections. It famously performed comparably to human specialists in trials.
Wow, comparable to specialists. That's impressive.
It was. And commercially, XCON was a big one, developed by Digital Equipment Corporation, DEC, in 1982. It configured complex computer systems based on customer orders, saving DEC millions. It showed AI could have real business value.
So expert systems brought AI into the real world, solving specific problems. But then, another winter. The second AI winter in the late 80s, early 90s. Why didn't the success of expert systems prevent that?
Well, the expert systems themselves ran into limitations. That brittleness we mentioned, it was a major issue. They worked great inside their narrow expertise, but step even slightly outside it, and they'd often failed completely, sometimes giving nonsensical answers.
Ah, so they didn't have common sense or broader understanding.
Not at all. And the knowledge acquisition bottleneck was another huge problem. Getting all that specialized knowledge out of a human expert's head and encoding it accurately into rules was incredibly difficult, time-consuming, and expensive.
Right, extracting expertise is hard.
Very. So while some systems were successful, the hype cycle turned again. The limitations became clear, enthusiasm waned, and funding got tighter again, leading into that second AI winter.
So another roadblock. But interesting things were happening beneath the surface during this period, right? Neural networks started making a comeback, and ideas about agents began to form.
Exactly. While symbolic AI was struggling, connectionism, the idea of modeling intelligence using brain-inspired neural networks, saw a major resurgence. A key factor was the refinement of the backpropagation algorithm around the mid-80s.
Backpropagation, what did that allow?
It provided an effective way to train networks with multiple layers, allowing them to learn much more complex patterns than earlier neural nets could. This, combined with gradually increasing computer power, let researchers like Geoffrey Hinton, Jan LeCun, Yoshua Bengio make real progress.
The godfathers of deep learning, as they're sometimes called now.
Indeed. And at the same time, you start seeing formal concepts related to autonomous agents emerge. Carl Hewitt's actor model from the early 70s, though focused on concurrency, described computation in terms of autonomous actors sending messages to each other. That was a precursor idea.
Autonomous entities communicating. Sounds like agents.
It has that flavor, definitely. Then, more explicitly, in the early 90s, Yoav Shoham introduced agent-oriented programming, AOP.
AOP, what's the core idea?
The idea was to program systems by defining agents that have explicit mental states, things like beliefs about the world, desires or goals they want to achieve, and intentions or plans to fulfill those desires.
Beliefs, desires, intentions. That sounds very human-like for software.
It does, and that led directly to the BDI model Belief Desire Intention, developed by Michael Georgiev and Anand Rao around the same time. It provided a popular architecture for building rational agents that act purposefully based on these mentalistic concepts.
Okay, a framework for building rational agents.
And this tied into the growth of multi-agent systems, or MAS.
The systems with lots of these agents interacting.
Exactly. The need was growing to handle more complex distributed problems. How do you get multiple agents to cooperate? How do they coordinate their actions or negotiate or even compete effectively? Research in MAS focusing on these interactions and also on situatedness agents embedded in and interacting with an environment really took off. People like Michael Wooldridge and Nick Jennings were key figures here.
So we're moving from single programs to these interacting, sometimes embodied agent communities.
Yeah.
This feels like it's setting the stage for the modern era. What happens from the early 2000s onwards?
Well, the early 2000s really see machine learning become dominant. Supervised learning, unsupervised learning, these become the workhorses. And we see AI agents entering the home in a big way. The iRobot Roomba.
Yes, the robot vacuum cleaner. An autonomous agent cleaning floors.
A very successful one. Then, the DARPA Grand Challenges, 2004, 2005, 2007. These competitions for autonomous vehicles were absolutely massive catalysts for self-driving car technology.
They really pushed the boundaries, didn't they? Even if some early ones didn't get very far.
They certainly did. Huge progress came out of them. Then, think about strategic games. IBM's Watson winning Jeopardy! In 2011, a huge feat of natural language processing and knowledge retrieval.
Right, understanding those tricky Jeopardy clues.
And then DeepMind's AlphaGo beating Lisa Dahl at Go in 2016. That was a watershed moment for deep reinforcement learning, showing AI could master a game with more possibilities than atoms in the universe largely by teaching itself.
That felt like science fiction becoming reality.
It really did. And around the same time, or slightly earlier, 2012, AlexNet absolutely smashed the ImageNet competition using deep convolutional neural networks. That really kicked off the current deep learning revolution, especially in computer vision.
Suddenly AI could see much better than before.
Dramatically better. Then came the transformer architecture in 2017. From that paper, Attention is All You Need. That became the foundation for the large language models, the LMs, that are everywhere now. Generative AI.
Right, the technology behind things like ChatGPT.
Exactly. And recognition followed. Hinton, LeCun, and Bengio got the Turing Award in 2018 for their work on deep learning. And all through this, we've seen conversational agents like Siri and Alexa become commonplace, leading up to today's incredibly capable generative models.
It's just been an explosion in the last, say, 10, 15 years. It feels like warp speed compared to some earlier periods.
The pace has definitely accelerated dramatically.
And woven through this whole technological story, as you mentioned earlier, there's always been this philosophical side, right? The debates about what it all means.
Absolutely. They've always been there. From the early days, you had the strong AI hypothesis, the claim that a sufficiently complex AI wouldn't just simulate a mind, it would be a mind, it would be conscious.
A controversial idea.
Very. And challenged powerfully by arguments like John Searle's Chinese room argument in the 80s, which questioned whether symbol manipulation, no matter how complex, could ever equal genuine understanding.
Right, the idea that syntax isn't semantics.
Exactly. And philosophers like Hubert Dreyfus were critical much earlier, especially of the symbolic AI approach. His 1972 book, What Computers Can't Do, argued that rule-based systems could never capture the intuitive, embodied nature of human intelligence.
So this tension between what we can build and what it truly means to think or understand, it's been there all along.
A constant, fascinating counterpoint to the engineering and the code.
So looking back over this whole sweep of history, ancient myths, logical machines, golden years, winters, agents, deep learning, what's the big picture, the main trajectory?
I think the key thing is seeing those cycles. Immense optimism, hitting limits, reassessment, then new breakthroughs often from unexpected directions. Like the resurgence of neural nets after the symbolic era struggled. It shows the field's resilience and ability to evolve.
It's not a straight line up, is it? More like waves.
Definitely waves. And it underscores that this whole quest is a really deep interplay between human dreams, philosophical questions, and hard-nosed engineering and scientific discovery.
And for you listening, the takeaway really is that this journey of AI is this incredible, centuries-long story. It's about that persistent desire to create intelligence, driven by curiosity, enabled by technology, and constantly pushing us to ask what intelligence even is.
Which leads to the final thought, maybe, considering this long, winding path. What does define intelligence, really, especially as our creations get more capable? And what's the next big shift going to look like? We've had symbols, we've had connectionism. What's next?
And crucially, what ethical questions become unavoidable as these systems weave themselves ever deeper into our lives? Lots to think about.
Definitely. Plenty to explore further, maybe digging into some of those names and ideas we touched on. It's a story that's still very much being written.